So we've gone through all these different types of reactions. And the first thing that we have to do if we want to predict the products of a reaction is predict what type of reaction will occur. From there, if I know it's going to be a combination or I know it's a single replacement, now we kind of know how to find the products. Now we've gone through each type of reaction in detail, but if you throw everything together, how can I predict what type of reaction will occur? And so in general, these combination reactions are also called synthesis. The ones that we'll focus on will probably have two elements on the reactant side. And the key then is that there's one product. There's one single compound on the product side. Now, technically, a synthesis or combination could also be like small compounds that join to make one bigger compound, but sometimes then it's a little harder to predict the identity of that compound. So we'll stick to combination reactions that look really similar to this, where if you've got two elements, you're just going to join them to make a compound. Magnesium plus oxygen will make magnesium oxide. Now again, when we make the magnesium oxide, we put the symbols together and then we check the charges to write the final formula. So I'm going to join magnesium and oxygen, and then it's a +2, -2, and I know it's neutral. So once I write my product, then I can go back and forth and balance as needed. The key to a decomposition is that there's only one reactant. There's only one compound on the reactant side. And that one compound will break apart into smaller products. Now again, the ones that we'll kind of focus on will look like this. Mercury oxide will break apart to form mercury and oxygen. Now it also could be a big compound that breaks apart to form lots of little compounds. But again, sometimes that's a little harder to predict, and we would save that for a second-year course. So we'll focus on combination and decomposition reactions that involve elements, either elements joining to form a compound or a compound that's breaking apart into its elements. Now, once I separate the elements of the original compound, then you just have to check for any diatomic elements, such as oxygen, which then would mean I'd have to balance it. But now that should be the easy part. I think we're getting good at balancing. Then we have the replacement reactions. I feel like these contain the most work. There's the most detail that has to go into these replacements. How do I pick out a single replacement? When I write the formulas for my reactants, there will always be a single element. There's always one single element on the reactant side, and then it's reacting with some kind of a compound, often in solution. An element and a compound. Now there's a couple rules. We said rule number 1 is that like charges can switch. So you have to maybe find the charge of your single element. So I'd say, well, magnesium is a +2. And then I'm going to find the charges on the elements in my compound. +1, -1. So it's super handy to have your periodic table nearby because most of these charges should be on there. Okay, so now that I know my single element is positive, it would like to replace the other positive. So then rule number 2 was we need to check the reactivity chart. I will give you that reactivity series, the reactivity chart, for any test or quiz where you will need it. And that's where I have to see if this is even an option. Magnesium needs to be more reactive than hydrogen. If it is, then the replacement is a go. Then I would switch magnesium and kick out hydrogen. And once you write your final products with the single element, we need to check for a diatomic. It might not always be a diatomic, but I at least need to check, is my single element diatomic? And with my final compound, I need to check the charges so that I can make sure I'm writing it properly as a nice neutral compound. From there, we just balance it. There's a lot of work to that though, right? It's just a lot of rules. The way to see the single replacement jump off the page though is that when you write the formula for your reactants, you're going to have a single element and a compound. Then the work begins. I got to check all the charges on the reactants. And then once I know who's going to switch, I got to check the chart to see if that is even an option. My single element needs to be more reactive than the one it's going to switch with. Awesome. From there, we've got the double replacement. The way that I look for a double replacement is that now when you write the formulas for your reactants, you're going to see two ionic compounds, often in solution, but it's two compounds. And that's how we get the double replacement. Now, the only rule here is just that like charges can switch. And so again, we're usually like switching the positive ions. So it might help to check the charges. Now, often the positive ion comes first in the formula. So here I would be looking to switch my potassium and my lead. But the key too is that when you do that new combination on your product side, check the charges. Your reaction won't balance even if you have one little formula written incorrectly, like, I forgot the 2 behind the iodine. The whole thing won't balance and it'll drive you crazy. So switch the potassium and lead, but then check the charges to see if you need any subscripts in your new products. You might also find yourself wanting to check the solubility chart. Maybe I'll put that in here too. For the phases, you can check the solubility chart, which I will also give you on any test or quiz where it's needed. But that might help you if you're not sure of the phase on one of the products. But often one product will either be a precipitate, which is a solid, some kind of a gas, or water. And the other product will be ionic, some kind of an ionic compound that now is in solution, an ionic solution, something aqueous. But usually the other product is something that's not aqueous, like a precipitate, which is a solid, water is a liquid, or some kind of a gas. And then finally, our combustion. Most combustions will have some kind of a carbon compound reacting with oxygen. The products are always the same. The products are carbon dioxide and water. Oh, okay. So most combustions look like the first one, the reaction of methane and oxygen to produce carbon dioxide and water. Now, technically, I think we also mentioned that. I mean, a combustion could be anything that's burning in oxygen. And so this carbon plus oxygen forming carbon dioxide could fall in this combustion category, but you could also call it a combination. Or synthesis reaction, where it's two elements that are joining to make one product. So if you can get the reactants down on paper by looking at what type of reactants you have, that should indicate what type of reaction will occur. And from there we can do a replacement, or we can do the synthesis or the decomposition. We can figure out the products. Now this last question here, number 24, is kind of backwards in that they give you this chart and they're telling you the products, And they want you to go backwards and figure out what the reactants could have been. Probable reactants. Ugh, weird. Okay, well, let's see if we can figure some of these out. So if my products were HCN and Na2SO4, that's like hydrogen. CN is cyanide. It's a polyatomic ion that would be on your chart, -1. +1, and sulfate is a -2. I've got two products that are both compounds. I'm wondering if this would have been a double replacement. What if I put a DR in here? Where maybe if this was a double replacement, I could kind of go back and switch my positive ions again. So that maybe the original reactants were something like sodium with cyanide, and then hydrogen with sulfate. And I'd have to go back and check all the charges again. +1, -1, +1, -2. Okay, so I need 2 hydrogen. But those products would be pretty typical if this would have been a double replacement. So if I kind of replace those positive ions again, I could go backwards and say that maybe the reactants would have been like sodium cyanide and hydrogen sulfate. Interesting, huh? All right, let's try another one. What if I only have one product, and that one product is just a compound of 2 elements? Magnesium nitride. Well, could this have maybe been like a synthesis or combination? What if the original reactants would have just been like magnesium plus nitrogen? Now I would have to check my chart or my periodic table because I think we marked it in. Nitrogen is a diatomic element. And then of course when I made my new combination of magnesium and nitrogen, I would have checked the charges again. And that's how we got the Mg3N2. When I check my charges, oh yeah, I would need 3 magnesium and 2 nitrogen. But maybe this was some kind of a synthesis. Obviously, I'm not balancing them, by the way, because I guess I'm not really asked to. Use the model for predicting products of reactions to instead predict the probable reactants and complete the table. Yeah, it doesn't ask me to balance them, so maybe I won't. Something like the third one. Ooh, what if my products are just carbon dioxide and water? Oh, I think I got this one. I bet it's a combustion. Which in that case, the reactants would have for sure been oxygen and something containing carbon. Some kind of a carbon-hydrogen compound. And one of the examples that they've used a bit is that CH4. But it could have been anything. Any carbon-hydrogen compound would burn in oxygen to produce carbon dioxide and water. I bet that's some kind of a combustion that would give me those products. The fourth one. My products are copper and zinc nitrate. I am seeing a single element. So I'm wondering if this would have been my single replacement. Where often copper's charge is +2 and zinc is also usually a +2. Now with these guys being transition metals, I would have told you the charges. But my single element is positive, so it could have come from a replacement with the zinc. And so maybe the original reactant would have had like zinc being single, and it would have reacted with copper nitrate. the formula would have been pretty similar because copper and zinc are both +2. So I would have needed 2 nitrates. Maybe I can like reverse the replacement and say, yeah, if that was a single replacement where the zinc replaced the copper, then yeah, I would have gotten copper metal and zinc with nitrate. Okay, I kind of see where this is going now. All right, and the last one, what if my products are the element sodium and, get that out of there, the element nitrogen? Well, it's 2 individual elements. Maybe it came from a decomposition. If this came from a decomposition, then the original reactant would have been like sodium nitride. Now I'd have to check my charges. Together as a compound, sodium is +1, nitrogen is -3. Whoa, so I would have needed 3 sodium, which then obviously this is not balanced. So I'd have to go back and forth and balance it a little bit. But maybe the original reactant was sodium nitride. That would then break apart into elemental sodium and nitrogen gas, which is diatomic.